On to electrical power. Electrical power is equal to the product of current and voltage. So power is the rate at which energy is used. Okay, keep that in mind. The rate at which energy is used by a resistor in the circuit specifically. So if there's a light bulb that's rated at 40 watts, that watt is the changing of the energy per second. The higher the wattage, the quicker it changes that energy. So that means it requires more and more energy. Unless it's in a superconductor, a charge moving in a circuit expends energy. This may result in heating the circuit or in turning a motor. Electric power is the rate at which electrical energy is converted into another form, like mechanical energy, heat, or light. Mechanical energy would be getting something to move. So maybe a record player or a CD player. Plugging it in, giving it power, allows it to spin the turntable. Electric power is equal to the product of current and voltage. So power equals current times voltage. If voltage is expressed in volts and current is in amperes or amps, then the power is expressed in watts. 1 watt equals 1 ampere times 1 volt. Well, let's take a look at that mouse. What's he trying to tell us over here? So 1 watt equals energy per second. Energy per second. 1 joule per coulomb, which is a voltage, which is the voltage. And the current is measured in 1 coulomb per second. If you line up the voltage times the current, you get 1 joule per second. Joule is the unit for energy. Second, dividing it by a second makes it a rate, so it's 1 joule per second, and that's what a watt is. The power and voltage on the light bulb read 60 watts, 120 volts. The current that would flow through the light bulb is, we're going to use that same equation, P equals I times V. Rearranging the equation, we get I equals P divided by V. 60 divided by 120 equals 0.5 amps. A lamp rated at 120 watts, operated on 120 volt line, will draw a current of 1 ampere. 120 watts equals 1 amp times 120 volts. A 60 watt lamp draws 0.5 ampere on a 120 volt line. Solid state lighting may soon make conventional light bulbs obsolete. Watch for the progression of LEDs from flashlights to automobile headlights. We're already seeing that. If you an LED, that's a light emitting diode. It's a type of resistor. If electricity comes in, then it emits light. That's its function. So it's not emitting heat like a regular tungsten light bulb. Instead, it's just light. So the LEDs are cool when you touch them. Chances are if you buy some Christmas lights or Halloween lights or whatever, you're going to buy an LED light bulb now. You have to do a little bit extra looking if you want some of the old-fashioned ones. The old-fashioned ones put off heat, so there's kind of a danger, especially if you're putting them inside on a dead tree. There's a risk for fire there. So it's preferred to get an LED light bulb, which there's still some risk, but it's definitely dropped tremendously because the LEDs are just emitting light. They're not emitting heat. For me, I have some of the old-fashioned light bulbs outside around some of my plants that don't handle the cold so well. And I've set up a circuit that turns on when the temperature gets to 38 degrees and then turns off when the temperature rises up to 50 degrees. So that way at nights when the temperature drops really low, those tungsten Christmas lights turn on and keep the plant nice and warm and surviving the cool winter. Kilowatt is 1,000 watts, and a kilowatt hour represents the amount of energy consumed in 1 hour at the rate of 1 kilowatt. Where electrical energy costs 10 cents per kilowatt hour, a 100 watt light bulb burns for 10 hours for 10 cents. Okay? read that again. Pause it, go backwards, because that can seem kind of confusing at the first quick read. A toaster or iron draws more current and therefore more power, which costs several times as much to operate for the same time. So your high efficiency appliances are designed to use less current, so that way it's not using up as much of that energy as quickly. Therefore, it's going to draw less energy from your energy generating plant, which is good for the environment, first of all, and it's good for you because it's cheaper to run that. All right, let's think about this. Pause this and try this question. How much power is used by a calculator that operates on 8 volts and 0.1 amps? If it is used for 1 hour, how much energy does it use? Think about it. Pause it. There we go. Power equals current times voltage. So the power is 0.1 amps times 8 volts gives us 0.8 watts. And then energy is power times time. 8 watts times 1 hour equals 0.8 watt hours, or 0.008 kilowatt hours. Kilo is just the metric prefix. That means times 10 to the third. So if we're going from the watt to the kilowatt, we're making this number smaller, so it goes left. All right. Will a 1200 watt hairdryer operate on a 120 volt line if the current is limited to 15 amps by a safety fuse? Can 2 hairdryers operate on this line? Pause it, try it, work it out. All right, so one 1200 watt hairdryer can be operated because the circuit provides 15 amps. 15 amps times 120 volts gives us 1800 watt. So there's extra energy available. That's good news. If there's more energy than is available, then the fuse or the circuit breaker is going to break off. And that's a safety precaution to prevent your damage to your hairdryer or vacuum or whatever. But there's inadequate power to operate 2 hairdryers with a combined power of 2400 watts, because 2400 is a lot greater than 1800. In terms of current, 1200 watts divided by 120 volts gives you 10 amps. So the hairdryer will operate when connected to the circuit. But 2 hairdryers will require 20 amps and will blow the 15 amp fuse. In your car, you have these fuses, and the fuses are part of the circuit. And if more current is going through the circuit than your radio or your headlights or your lane assist can handle, then the fuse will break apart. It'll burn up. Concept check. How can you express electric power in terms of current and voltage? All right, so your homework is to ask the people you live with to look at the electric bill. What are you billed in? Are you billed in watts, current, voltage, watt hours, kilowatt hours? What is it? Go look at your electric bill. Try to make sense of it.